Hello, it's stat134, lecture 18. Today we're going to do a midterm review and go through some questions that people had. The first question is going to be involving a geometric type expectation variance calculation. The second one is going to involve a joint distribution and the convolution formula. Then we're going to do an inclusion-exclusion type calculation. Then we're going to do what's called a hypergeometric negative binomial, which is negative binomial-like, but that we're drawing with without replacement. We're not really going to do this Balaji's question here, but I am going to include a bonus indicator example at the end. So let's start with Emma. So we have X is the number of Bernoulli P trials required to produce at least one success and at least one failure. Should be fairly clear what the formula is for this distribution, since, for example, if X is 3, it's either P squared Q or Q squared P, but not PQP, because if it was PQP, you would have stopped after Q, because you would have had at least one and at least one Q at that point. So I also want to mention that this is not one of our named distributions, nor is it some combination of a known distribution. It's really just related to a geometric. To calculate the expectation, just using the definition, I just start off with the definition, and my goal is to write this in terms of the expectation of a geometric P and a geometric Q. And so this is fairly straightforward. The variance calculation, however, is more complex. I'm going to calculate the expectation of X squared, and so let me just introduce a little terminology here. So let's say that Y is geom P. So I'm going to try and express the expectation of X squared in terms of the expectation of Y squared. So let's see how that happens. So it comes down to the third line here. The first summation here you see as the expectation of Y squared. And to calculate that, I use the fact that the expectation of Y squared is the expectation of Y quantity squared plus the variance of Y. And that allows me to write this summation here as 1 over P squared plus 1 over P divided by P squared. And I can do something similar with the second summation here, which is a geom Q thing. So that's the main idea here. I wouldn't expect something this complicated on the midterm, since you only have 45 minutes. On to Justin's convolution formula problem. We first just verified the convolution formula. That's very straightforward. And then we looked at an example where we find the probability that the sum of numbers on 4 dice is 8 by taking X to be the sum of 2 of the dice and Y the sum of the other 2. So I've written out the distribution for both X and Y and put them in the margins here for this joint distribution of X and Y, of which we're interested in the highlighted cells. So there are 5 such cells corresponding to the probability that X plus Y is 8. And I find those probabilities, X and Y, are independent, so it's a product of the marginals. Then we did, I'm sorry, I forgot your name, Lindsay's problem. So Lindsay, wanted inclusion-exclusion type formula, and I threw in a matching problem as well here. So 10 people throw their hats in a box and randomly redistribute the hats among themselves. Assume every permutation of the hats is equally likely. Let n be the number of people who get their own hats back. So the part that involves the inclusion-exclusion is the third part. So in the third part here, we write the probability that no one gets their hats back as 1 minus the probability that at least one person gets their hat back. And the probability that at least one person gets their hat back, in other words, the union of A1 to A10, we find that using the inclusion-exclusion formula. And then it's a matter of writing out what these probabilities are. So the probability of a person getting their own hat back is 1 over 10. The probability of the first person and the second person getting their own hat back is 1 over 10 times 1 over 9, and so on. Now, the number of terms I less than j is precisely 10 choose 2. We don't need also the case j greater than I, so that's why I'm dividing by 2 here, and that makes the answer quite pretty. So here's an example of a without replacement version of the negative binomial for Tony. So here the probability that x is greater than x, this is the chance that the third ace is not before the xth draw, which means that there are either 2, 1, or 0 aces in x draws, and I can find those probabilities straightforward using hypergeometric formula. The probability that x is x, I can either use part I, but more straightforward is perhaps more direct, I should say, is to realize the probability that x is x is the probability that I have 2 aces in x minus 1 draws and an ace in the xth draw, and I can find each of, so I can use the multiplication rule here and write out each of these probabilities. So the first is just a straightforward hypergeometric formula, and the second, remember, I have 2 aces left over, given that I've already have 2 aces in the first x minus 1 draws, and there are 52 minus x plus 1 cards left. So to compute the expectation, I write x as 3 plus the number of 48 indicators corresponding to the non-aces. So I1 is 1 if the first non-ace is before the third ace. So this is similar, to find that probability, it's similar to the concept test. You can just think of it that there are 5 relevant cards here. You have your 4 aces and your single non-ace. It's equally likely that that non-ace is either before the first ace, between the first and second ace, and so on. There are 5 slots that it can be in. So the probability that your non-ace is before A3 is 3 out of 5. To find the variance, we need to calculate the probability that the first and second non-ace is before the third ace. So the probability that the first ace is before the third ace, we've already calculated. The probability that the second non-ace is before the third ace, given that the first ace is before the third ace, is 4/6. To see that, just think that given that the first non-ace is before the third ace, there are now, so there's 6 relevant cards that we're dealing with here, 2 non-aces and 4 aces, and I'm told that the non-ace falls, the first non-ace falls before A3. So I have 1, 2, 3, 4 slots that the second non-ace can fit into, equally likely. So it's 4 out of 6. and then we can compute the variance of x straightforwardly. So Balaji's problem I'm going to not do, but I will do an extra indicator problem. So suppose you have 100 balls, color red, blue, and green for a total of 300 balls. There are 100 bins and 3 balls are placed in each bin. Let x be the number of bins that have 3 balls of the same color. Find the expectation of x and the variance of x. So x is the number of bins that have 3 balls of the same color. So I'm going to write x as a sum of 100 indicators, where I1 is 1 if the first bin has 3 balls of the same color. And that probability P1 is just a straightforward hypergeometric. So let's say that the color is red for a moment. So the probability that I have 3 red balls in the first bin would be 100 choose 3 divided by 300 choose 3. But I have 3 possible colors, so I have to multiply this by 3. Now, to find the variance of x, I'm going to have to find the probability that the first and second bin have 3 balls of the same color. Let's call that Q12. So the probability that the first bin has 3 balls of the same color we've already seen, and now I need to multiply that by the conditional probability that the second bin has 3 balls of the same color, given that the first bin has 3 balls of the same color. But the second bin could have the same 3 balls of the same color as in bin 1, in which case that would be 97 choose 3 over 297 choose 3. Or it could be a different color, like whatever the 2 other colors are, blue or green. And so for each of those, it's 100 choose 3 over 297 choose 3. And I multiplied by 2 because there are 2 blue or green. And then I just calculate the variance of x straightforwardly from there. So I hope you feel things are starting to come together. You worked really hard so far this semester, and I'm sure you're going to do great.